So now we're going to go through an application of the hyperbola. And one application of the hyperbola is a flight path of an object in space. Now, as we read this, there's a lot of information that's given to us. I'm going to highlight the information that's important. So it says, assume that an object enters our solar system and we want to graph its path on the coordinate system with the sun at the origin. And the x-axis is the axis of symmetry. Give the equation of the flight path of the object using the given information. The x-axis as the axis of symmetry is going to be our transverse axis. So our transverse axis is going to be horizontal. And the other information that it gives us is our asymptotes, because it says the object enters along the path y equals 2x minus 2, and its closest position to the sun is 0.5 astronomical units away, and then it leaves the solar system along the path y equals negative 2x plus 2. So if we look at the picture, the sun is going to be at the origin. It also tells us that the sun is one of the focus points. So I'm going to label the sun as also the focus. So I'll put S is equal to F to remind us that that's the focal point. Now it tells us that we have a path of 2x minus 2. Negative 2 would be my value of b, so it crosses the y-axis at negative 2, and it has a positive slope, so it's going to go up, left, to right. So it's going to pass through at negative 2. So this is y is equal to 2x minus 2. And then the object leaves the solar system on the path of negative 2x plus 2. That means it has a positive y-intercept with a negative slope. So now that's going to look like this. If we were to set those two equations equal to each other, 2x minus 2 is equal to negative 2x plus 2, we would find that they cross at the point 1, 0. And that's where our asymptotes cross, so that's going to be our center. So our sun is at a focal point, so that means the distance from the center out is my distance of c. So I know that c is going to be 1. From 1 to the origin, from 1 to 0, the distance of c, which is 1. Now, it says the path of the object, it comes in along the line 2x minus 2. So the object comes in, and then it leaves on the path negative 2x plus 2. And it passes within 0.5 astronomical units of the sun. So that would be this distance from here to here would be 0.5, which means this distance from here to here would be 0.5. So that tells us that A, which is the distance from the center to the vertex, is 0.5. So now we're going to use c squared is equal to a squared plus b squared to find our value of b. So I'm going to have 1 squared is equal to 0.5 squared plus b squared. So b squared is going to be 3/4 or 0.75 if you want to use decimals, because 0.5 squared is a quarter. And if I take 1 minus a quarter, that gives me 0.75. So b is equal to the square root of 0.75. Now, because my transverse axis runs horizontally, and I have a center at 1, 0, I know my x term is going to come first, and I'm going to have x minus 1. That's my shift over to the center from 0, 0 to 1, 0. My value of a is 0.5, so I'm going to have 0.5 squared minus y minus 0 squared over b squared, which is 0.75 the square root, that's my b, and then I square that, which is equal to 1. So this is the equation of the hyperbola that represents the path of this object in space as it comes in towards the sun and then slingshots back out.